A single-turn LLM call is easy. You send an instruction, the model reads it in an isolated environment, and it executes exactly what you asked. But a 20-turn agent session is a completely different environment. By turn 17, that clean instruction is buried under a growing transcript, tool outputs, and summaries. When it misbehaves, we blame the model, assuming it hallucinated, and buy a smarter upgrade. This diagnostic focus is misplaced. When we examine the traces of these failures, we find the model's path of inference often remains sound. It is simply processing the wrong information. The failure is actually occurring in the memory orchestration layer built around the model. The agent is reasoning perfectly, but it is doing so over a corrupted, stale, or semantically noisy memory state. This error accounts for the majority of production-level issues. Memo's 2026 analysis attributes 65% of enterprise AI agent failures to context drift and memory loss during multi-step workflows. Laban and colleagues plotted agent performance against conversational turn count. Performance is stable early on, but approaches a steep cliff at 20 turns, dropping 39%. This signals a surge in unreliability, as recent data pushes early instructions out of focus. To fix this, we have to split the definition of a hallucination in two. A factuality hallucination is what happens when a model generates a fake real-world claim directly from its training weights. A faithfulness hallucination occurs when the model's output diverges from the specific instructions or context you provided in the prompt. This second category, the multi-turn breakdown of memory, is known as context drift. Until an engineering team learns to differentiate structural drift from a genuine hallucination, their diagnostic efforts will remain focused on the wrong layer of the architecture. A common misconception in agent design is that a 200,000 token context window gives the model 200,000 tokens of active, reliable working memory. When you treat the window like an infinite hard drive, you get instruction inconsistency. This is the agent that follows a strict JSON-only rule for 9 turns and then suddenly replies in conversational plaintext on turn 10. The JSON instruction is technically still in the prompt, but it has been evicted by recency as relevance. The LLM's attention mechanism heavily weights the newest local tokens. As chat history piles up, the original constraint physically fades from active computation. This is an engineering parallel to a concept introduced by economist Herbert Simon in 1947, bounded rationality. Under severe long context load, an LLM becomes the ultimate satisficer. It stops calculating the optimal global answer across a 100-turn history. Instead, it scans the immediate local context and outputs the first plausible sequence that matches the tone of the last few tokens. The model ignoring your system prompt is a fast and frugal heuristic deployed to survive cognitive overload, rather than a failure of logic. The second symptom of drift is context inconsistency, where an agent confidently contradicts the external data you fed it. For example, writing code using an API that the retrieved manual clearly marks as deprecated. To understand why this happens, look at how physical structures handle missing pieces. If a void appears, it must be filled to maintain surface stability, even if the filler material is entirely mismatched. When a retrieval window is flooded with irrelevant semantic noise, the specific grounded fact the model needs is obscured. This creates a cognitive blind spot, a memory gap. Decades ago, psychologist Frederick Bartlett defined this as schema-driven reconstruction. When recalling information, a system does not leave a blank space where a memory should be. Instead, it generates a highly probable substitute based on surrounding patterns. Because the LLM lacks source monitoring, it is entirely blind to its own reconstruction. It cannot distinguish between a token it extracted from your trusted PDF and a generic token it just generated to patch a gap in its attention span. Without an external system explicitly tracking where facts come from, an overwhelmed model will instinctively smooth over its memory gaps using ungrounded priors from its training data. The most damaging symptom of drift is logical inconsistency, where an agent abandons its own chain of thought mid-task and executes a completely unrelated action. This breakdown maps directly to Daniel Kahneman's dual process theory of cognition. A standard LLM forward pass is a System 1 device. It is built to be a fast, associative, pattern-matching engine that predicts the next probable word. Complex agentic behaviors, like step-by-step planning, are essentially System 2 structures, rigid, deliberate scaffolds engineered to sit on top of that fast associative engine. But an agent's intent is highly vulnerable to perspective memory failure. When an influx of intermediate tool errors or bloated search results floods the context window, the original plan is physically displaced. The System 2 scaffold collapses under the token volume. This is why agents drift into endless, irrelevant task loops. They lose the deliberate thread of their intent and default back to cheap, reactionary pattern matching. You cannot prompt engineer your way out of context drift. You have to build deliberate, external architectural scaffolds that protect the model's attention. To solve source monitoring failures, you must externalize provenance. This means forcing the model to generate strict citation spans so the origin of every factual token is physically visible in the text. To prevent perspective memory decay, you implement a file-backed state anchor. This acts as a distinct, stable substrate that stores the original goal and the current step independently, completely isolated from the probabilistic decay of the main attention window. By appending this anchor to the very bottom of the prompt on every single turn, you create an inescapable loop. You force the model to explicitly reread its own intent right where its attention is strongest. Extracting state management from the LLM and placing it in an external file system is the only reliable way to immunize a multi-step plan against token displacement. The final bottleneck is the raw working memory limit itself. Unformatted transcripts simply carry too high a cognitive load for accurate retrieval. To solve this, production pipelines use an agent cognitive compressor, or ACC. Instead of feeding the agent a high-entropy stream of raw text, the ACC continuously summarizes prior turns, extracts key entities, and compresses them into dense, schema-tagged blocks of state. By feeding the model pre-indexed material, you allow it to bypass token overload entirely. It functions exactly the way a human expert uses long-term working memory to retrieve facts without intense mental effort. This newly scaffolded session succeeds because the model is finally operating on high-integrity data, rather than a decaying context window. To achieve production-grade reliability, engineers have to stop trying to fix the model's mind and start orchestrating its memory.